Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Marianne Freiberger. Imagine you could have a digital version of your entire body, which could help you and your doctors decide what lifestyle is good for you, predict what diseases you might get, and how best to treat them. So in short, what if you could have your very own digital twin? Now, this idea sounds quite sci-fi, but it's not quite as sci-fi as it sounds. There's a gigantic scientific effort called the Physiome Project, which is about piecing together a mathematical description of the entire physiology of the human body. And once this has been achieved to a sufficient level, digital twins will be a spin-off. Back in 2019, our friends at the Isaac Newton Institute for Mathematical Sciences in Cambridge ran a research program called the Fickle Heart, at which we met Steven Niederer. Steven was then a Professor of Biomedical Engineering at King's College London and has since taken up a new position at Imperial College as Chair in Biomedical Engineering. Now, Steven knows all about digital twins, and in this podcast we are going to revisit the interview we did with him back then. Steven tells us about the Physiome Project, about how the smartwatches and fitbits that many of us now own are the very first step towards a digital twin, and about how you can model individual human organs such as the heart. Also in this podcast, my colleague Rachel Thomas, who you will be hearing talking alongside myself, we will challenge each other to explain differential equations in 1 minute. But here's Steven Niederer explaining what he means by a digital twin.
So the digital twin concept is an idea which has been put forward, and it's kind of a very exciting idea, that each individual would have a digital replication of themselves, and that as more information was acquired about that individual, their mathematical representation will be updated. And the benefits of this are that it would provide a consistent framework for combining information from multiple different sources, but also it would allow a system which was able to anticipate the needs of the patient or the person prior to them needing them. So that we're no longer trying to treat people based on the way they are today, but trying to predict them in anticipation of how they might be tomorrow.
We met Steven last year at St Thomas's Hospital in London, where he does a lot of his work. And in this podcast, we'll find out more about that exciting digital twin idea. And also he'll tell us about a hugely ambitious endeavour called the Physiome Project, which is about linking together all the medical research there is about the human body, and which we were very pleased to hear might eventually put an end to the use of animal experiments in medical research. We'll find out how you can use maths to model different parts of our body, and as usual, we'll challenge ourselves to explain some maths in 1 minute.
You may have heard of the Genome Project, whose aim was to work out the entire DNA sequence of the human genome. It was a massive international scientific collaboration, and it took 13 years to complete. Now, the Physiome Project is not about our genes, but the physiology of the human body, and it's even more ambitious. As the Physiome Project website puts it very succinctly, the project is about putting Humpty Dumpty back together in a concerted effort to explain how each and every component in the body works as part of the integrated whole. And this is done, how else, through the use of mathematical models, as Steven explained.
So the idea of the Physiome Project was that we should be able to encode different parts of known physiology within mathematical models or within systems of equations. And by making modular models which represented different elements of physiology, we should be able to bring those together and integrate them into whole systems where we could start to simulate more complex emergent phenotypes.
Why do we need this effort to put Humpty Dumpty back together again? Medical research is hugely specialised. Entire labs employing a number of specialists may spend all of their time researching, for example, one single protein, how that protein is regulated, how it is made, where it sits in a cell, and so on. That effort might take years and take all the attention of the scientists involved. Now, such work is obviously essential if we're going to understand how our bodies work, but it's also essential to understand how different parts of our bodies work together. how a particular protein operates in the larger context of a cell, or how a cell functions in the context of an entire organ, and so on. It's not enough to just investigate all the individual parts, you also need to look at their sum. As Steven explained, the Physiome Project is about making that possible by providing a mathematical framework for linking research of different aspects of the body together.
So if everyone who's made their protein that they're very interested in, or their system of proteins that they're very interested in, and they've encoded those into a model, then they can put all of their experimental results into that model and then place that model or couple it to all the other models that all the other groups have made and see if it all makes sense when you add it all together. And that allows you to identify gaps that you say, this output from our model doesn't interact with the other models the way we expect, and that allows you to discover new things. So that's where you integrate all these different components together, and there might be emergent phenomena where multiple protein systems are all acting together to give you some cellular function, and that you only see when you combine everything together into one whole system. And again, no one group is going to do all the experiments to characterize that system fully, so a great way for sharing and reproducing your data is to encode it in a model that makes a very succinct way of kind of encapsulating all the measurements that someone's made.
Now, one great thing about having such an integrated system of models is that it can reduce the number of experiments you need to do. So put simply, traditionally, if you want to see, for example, how a particular cell reacts to a particular substance, as you might in the development of drugs, you would have to test that in an experiment. But if someone has already developed a very good mathematical model of the relevant processes within the cell, you might get an idea of how the substance influences them by using the model, so you might be able to do with fewer experiments. And this is why the National Center for the Replacement, Refinement and Reduction of Animals in Research is very interested in the Physiome Project.
So, when can we expect this gigantic project to be completed, wrapped up, finished? Well, perhaps never, but that's not a bad thing. It's simply a reflection of the complexity of the human body and the fact that we'll never stop learning about it.
The Physiome Project is a way of thinking about physiology as a complementary kind of complement to experimental results, where you try and say that we need to do these experiments but also encode all the physiology that we know in mathematical models. I don't think we're at any time in the near future going to be done measuring physiology and understanding physiology. So in that sense, it's not a completable project. However, there are kind of goals that individual groups set within that framework and in that context that people are aiming to achieve. So there are deliverables, but there isn't a global, we are finally done, mission complete thing that will happen.
We've talked a lot about mathematical models, but we haven't given much of an idea of what those models might be. So let's look at one particular example, the heart, which is what Steven has been working on. As with many other processes in the body, what we can most easily observe is change, for example, change over time or change over space. In the heart, two things we can observe is how the heart beats, that's how it rhythmically contracts and relaxes over time, and we can also observe the electrical signals that travel through it. In maths, change is described by differential equations. We'll look at them in a little more detail at the end of this podcast, but for now, let's just note that a model of the heart consists of a system of differential equations describing different types of change, and they're all coupled together to represent its overall function.
So obviously with any system of which we make a model, there are a spectrum of ways in which we can represent this with different levels of complexity. The work that we do tends to focus on simulating the electrophysiology of the heart and on simulating the mechanics of the heart, and we like to do this in models which capture the anatomy of the heart, both for the individual, if it's for a patient, or for this particular animal, if it's for experimental research. And so in that sense, the electrical models are a system of partial differential equations, which are coupled to a system of ordinary differential equations which represent the cellular function. Whereas in the mechanics, it's very similar, where we have, again, a system of partial differential equations which simulate the tissue mechanics, and then those are driven by systems of ordinary differential equations which capture the cellular physiology which is driving that cellular contraction, and that gets integrated up to simulate mechanics over the whole heart.
What is interesting here is that you need equations to describe what is happening in each cell, and then you also need equations to describe how that cellular function is linked up to result in large-scale function across the whole heart. Now, since the heart contains billions of individual cells, does that mean we need billions of equations just to represent each cell, and then even more equations to represent how these cells link up? Well, luckily we don't. There's a mathematical technique called finite element analysis, which allows you to break up a larger system into a manageable number of components that act as representatives for the many, many small components there actually are, and tells you how to solve your equations for this approximate system. It's a bit like building a wireframe model of the heart, and instead of considering all the cells in the heart, you only consider those that lie at the vertices of that wireframe.
So we don't represent all of the cells in the heart. We use what is the finite element method for solving our partial differential equations, and that the vertices of that mesh that we use for the finite element method, we have a cell model at that vertice, but that represents a volume of cells, which will be thousands or tens of thousands of cells in that one vertex.
Finite element analysis is a great example of the power mathematical tools can have. It is used in many areas, from designing buildings to designing sports equipment to designing planes. In all of these contexts, you are dealing with complicated objects made out of many parts, which you need to break up into manageable components. You can find out more by searching for the phrase finite element analysis on plus.maths.org.
Interestingly, it's also possible to make a model of an individual person's heart, which could be used by a doctor to make particular decisions. So, for example, pacemakers help the heart pump. Unfortunately, in 30% to 40% of patients, the pacemaker isn't effective. One reason for that might be that the pacemaker should have been put in a different position within the heart. So when it comes to fitting a pacemaker, the location is a really important thing to consider. Simulations of an individual patient's heart could help make the best decisions. Obviously, constructing such a comprehensive model of someone's heart isn't easy, as Steven explains.
As with everything, there are multiple challenges. So one of the challenges are that you need to be able to take a lot of clinical data. So that might be imaging data, it might be ECG data, it might be patient history data, or population data from things like the UK Biobank, and combine all of that information into a single representation. And so there is a challenge in how do you infer or determine the material properties or parameters in the model based on often noisy and maybe potentially inconsistent data that was recorded at different times into one representation.
What kind of parameters?
So that might be how stiff the heart is, how fast the electrical waves are propagated across the heart, what the heart rate is, how big the heart is. These are the type of parameters in very coarse terms that we're looking to determine from the clinical data. And then once we have made these models and inferred the parameters for that individual, we would then like to simulate those, make simulations to predict the outcomes of a therapy or a treatment as fast as possible, and we need to do that within a clinical time frame. So these models can't take a month, a week, even an hour to solve. We need to have these very fast, so ideally a doctor tends to like to have an interactive environment so that they can test different ideas, and so that's a positive. And so basically the models need to be fast enough and efficient enough to run within a clinical workflow so that you don't finish the simulation after the patient's already had their therapy.
So when will we see such individualised models in routine clinical use? When we talked to Steven, they'd just started doing pilot studies in specific research centres such as at St Thomas's and Johns Hopkins to serve as proof of the principle. The next stage is to do larger randomised clinical trials, and if these show that there is a meaningful impact on the outcomes for the patient, and if the health economics make sense and all the required standards are met by these systems, then they could be rolled out more widely. So it'll be some time yet. Doctors using the outcomes of mathematical models to inform their clinical decision makings is pretty interesting. What do you think of the idea, Marianne?
Well, personally, I really like the idea of the doctor running a mathematical model to make decisions about my treatments or make diagnoses and so on. Because sometimes talking to a doctor can feel a bit like asking a black box. Like you go in, you tell them what your problem is, and they'll give you some sort of an answer without showing they're working. So you don't know where does that answer really come from. And personally, I'd feel a lot happier if there was a mathematical model that I could even go to look at if I wanted to, that is at the basis of that decision that was being made for me by the doctor.
I mean, our appreciation of that idea might be because we're mathematicians, but also I think it sounds like there's some really clinical and scientific benefits to it. But what about this exciting idea of having a digital twin so that rather than having a model of just a part of our body, we'd have a model for our entire body that could be continuously updated with new information as it comes along? Is that going to happen anytime soon?
I think it's about resolution. So you may say that, and people's definitions. So a digital twin could be something which is a relatively simple mathematical model which is continually updated based on something like a Fitbit or Apple Watch measurement. And that could be a very, very simple system. And so you could say that was a digital twin, which might be two differential equations coupled together, and just those parameters are updated, and it's not very predictive, but it is a mathematical representation of you, which can make some prediction. So I think there's what you might see as a total virtual, fully rendered movie equivalent version of you with everything covered in particular detail.
As a hologram.
As a hologram is unlikely to happen in the near future. Whereas I think we'll start to see these relatively simple models very soon. You may not even be aware that they're there, though. That it might be encoded or embedded in some kind of wearable device. And within the hospital, you will, I think, increasingly see these different systems being adopted for guiding therapies first. And as they're used for guiding more and more therapies, then they will become more the norm. But I would say I could not hazard a guess as to when they will become routine that we will all have a digital twin.
So we're now moving to the maths in a minute part of this podcast. I am going to challenge Rachel to explain what differential equations are in 1 minute. Are you ready? 1, 2, 3, go!
Okay, imagine you're driving down the motorway at a steady speed of 70 miles per hour. If you arrive at your destination in 2 hours, then you can easily work out that you've travelled a distance of 140 miles. What you've done there without noticing is solve a differential equation. Speed is the rate of change of distance over time. And from observing this rate of change, you've worked out how the quantity that's changed, distance, how much it changed at the end of your journey. So this, put simply, is what differential equations are all about. When we look at the world around us, often what we see and what we can measure is change. How some quantity x changes over time or space, or perhaps with respect to some other quantity y. You can often write down a mathematical expression describing this change of x with respect to y, and that's what's called an ordinary differential equation. Solving the differential equation amounts to working out, from the rate of change of x with respect to y, the value of x for every possible value of y. So in our example, x was distance and y was time, and the rate of change of distance with respect to time was a constant 70 miles per hour. The solution to the corresponding ordinary differential equation is that the distance travelled at a particular time t is just equal to 70 times t, where t, time, is measured in hours.
Yeah, well done. You did that in just about a minute. But I did notice that you cheated because you talked about ordinary differential equations. So are there also non-ordinary differential equations?
Yes, you're right. In an ordinary differential equation that I mentioned, we only consider the rate of change of a quantity with respect to one other quantity. So in our car example, we were considering the rate of change of distance only in respect to one other quantity, time. So in the language of mathematics, speed is known as the first derivative of distance with respect to time. Acceleration is the rate of change of speed with respect to time, which also makes acceleration the second derivative of distance with respect to time. This is what is meant in maths by higher orders of derivatives. What is called an ordinary differential equation can contain not just the first derivative of something with respect to that other quantity, in our case time, but also higher order derivatives. Now, you can also have equations relating the rates of change of some quantity with respect to several other quantities. So an example that's easy to think of is you might consider how a quantity x changes as you move around in space. You might need to consider its rate of change with respect to all three directions of space. How scared I feel in terms of vertigo changes much more dramatically if I move up than if I move left or right. When this happens, you are dealing with a partial differential equation, which can involve partial derivatives of all orders.
That's it for this PLUS podcast. We would very much like to thank the Isaac Newton Institute in Cambridge for putting us in touch with Steven Niederer, who organised a workshop there in 2019.
The music in today's podcast came from Ollie Freak, and the track was called Space Power Facility. You can find more of Ollie's music on SoundCloud. I'm Rachel Thomas.
And I'm Marianne Freiberger. Thanks for listening, and bye-bye.